Welcome to another video. So this is video number 3. And before I start doing other things in linear transformation, there are some transformations that are very important and they come up frequently, and I would like to talk about them because they are the most used: rotation, reflection, and projection. Now, each of these transformations are linear transformations, okay? And I'm going to try to help you see that they are linear transformations. And that's going to be it. Let's get into the video. If you recall, in the last video, I was talking about a point moving away or being transformed or being moved to another point, and I said it was a linear transformation. Now, what I meant by a point was actually a vector, because you see, a vector can be defined by a point in R2. Look, if this is a vector, this is the end of the vector, okay? I know I put that there, but I just want you to see, you see this point? If I was just doing basic graphing, I would define this point as, I might say, hey, let this point be the point 3, let this be 2. So I define this point as 3, 2. Now, this is how we write vectors actually, because this determines the length of the vector is the magnitude, this squared plus this squared. You take the square root, that's how you know how long the vector is, right? And you can even tell the angle between the vector and the x-axis. Okay? And ultimately, the angle between the vector and the y-axis. So there's so many things that this guy can tell you about a vector. How long the vector is, in what quadrant the vector is, the angle it makes with the x-axis, you can tell depending on what these two numbers are. So when you do something to this point, you're actually doing something to the vector. Okay? Now, this is in R2. We're dealing with R2 just to simplify everything. So suppose there is some transformation that takes a point and then rotates the point. Now, in mathematics, rotation is counterclockwise. You must go this way. When you're doing rotation, don't follow the clock. When you go in the clockwise direction, it is a negative direction you're going. You always go, remember when we do quadrants, quadrant 1 is here. Quadrant 2 is here. You see, we're going this way. So whenever we do a rotation, we are imagining that you're going counterclockwise. Okay? Firstly, we don't know this angle here, although we can find it. Let's say, for just to generalize everything, I'm not going to use 3 and 2. Let me say I use letters A1 and A2. A1, A2. So clearly this is the one representing the horizontal axis. So I'm going to call this A1. I'm going to call this A2. So what I want to do is I want to rotate this vector. And by rotating the vector, I'm just changing the position of this point. When this vector rotates through an angle, let's say the original angle was alpha, and I want to add some more. And then, remember, the length does not increase. What changes is just the position of the end of the vector. So it's going to be the same length, maybe something longer, like this. But it is no longer these 2 points. The point has changed. It is now some point here, which I can call A1 prime. And some point here, which I can call A2 prime. Now, how can I find A1 prime, A2 prime, just because I have done a rotation? Well, it depends on by how many degrees or radians you have rotated the point or the vector. So let's say I've added, let's say theta. So what I've done now is I have done a transformation through an angle theta of the point A1, A2. What will be the new point. Remember, the only thing you're looking for now is you want a definition of this transformation. After we can write a formula for the transformation, it will now be your job to show whether this transformation is a linear transformation or not a linear transformation using those testing methods that I explained in the very first video. So I'm not going to show you whether this is, because there's a lot, you require a lot of paper to write it, but let's find what the result is going to be. So you're going to find something. You're going to find something, comma, something. Let's make it big. We're going to come back to this. Okay, now let's do some work. So the nice thing about what we have is that we learned trig and Pythagorean theorem and all that. That's what we're going to use. So we're going to say that the length of this line, we're going to call it r, because when you're doing a rotation, you're actually generating a circle. So this is more like the radius of the circle through which the point is going. Okay. Tap, tap, tap. And we said that the initial angle was alpha. So we don't want to be dealing with everybody and everything. Okay. So let's just use what we started with. We can write A1 in terms of the radius, because we know that from our trig ratio, if we try to find cosine alpha, it's going to be adjacent over hypotenuse, which is A1 over R. So we can say basically that A1 is R cosine alpha. Similarly, if you do the trig ratio for sine for this, you're going to end up with A2 equals R sine alpha. So we have these two guys here that are going to help us. Now, having obtained these two, we want to know what this new guy is, because this new guy has changed location. The zip code is now here. But we know that the angle is no longer alpha. The angle has changed to alpha plus theta. So the new angle, so this A1 prime is not R cosine alpha. It is R cosine alpha plus theta. And A2 prime, the new A2, this guy up here, is R sine alpha plus theta. Okay, we learned in trig that whenever you're adding angles and they're the argument of a cosine, you might as well rewrite it as R times cosine alpha plus theta using the angle sum formula for cosine is going to be cosine alpha cosine theta minus sine alpha sine theta. If you do the same for sine, the angle sum formula for sine is going to be, we write the R, this is going to be sine alpha cosine theta plus cosine alpha sine theta. This is supposed to be in parentheses, but I didn't put the parentheses because I want to distribute this R. I already gave this guy's R. This guy too also needs an R. So let's put R here. Okay, so everybody has an R. But our life is easy because of what we found initially. Okay, look, what is R times cosine alpha? Ta-da-da! It's A1. So I can actually cancel this guy out and write A sub 1. This guy's out. What is R sine alpha? R sine alpha is A sub 2. I can strike this guy out and write A sub 2. What is, ta-da-da, R sine alpha is still A sub 2. Take it out. A sub 2. And this is A sub 1. So whenever you do a rotation through an angle theta, notice that the only thing that survived, the only angle that survived in this, our final point, are all the thetas. The alpha doesn't matter. So we go here and say, whenever you rotate this point through an angle theta, the new point is going to be a sub 1 cosine theta minus a sub 2 sine theta. It's going to be a sub 1 cosine theta minus a sub 2 sine theta. When you want to find the other part of this, it's going to be a sub 2 cosine theta plus, or let's do 1 before 2. Since it is positive, I can switch the positions. Okay. So we have a sub 1 sine theta plus a sub 2 cosine theta. So this is a transformation. This transformation is called rotation. Okay? Do you think this rotation is a linear transformation? Well, you have to do the verifying yourself. So let's consider a reflection over an axis. Say, so we have this vector, we want to reflect it over one of the axes. So the first axis, let's just start with the x-axis. If you reflect it over the x-axis, what happens is this point comes down here. So it's more like the x-axis becomes a mirror. So you have this comes here. Okay? Now, notice that the value of x stays the same. So when you want to describe this new point, which is the image, a1 is still a1 because that's the value on the x-axis. So this is a sub 1. However, this a sub 2 was a positive number. Now you have that same number here, but it's now negative. So what you have here is negative a2. That is a reflection across the x-axis. So you can say that this is a transformation of a point a sub 1, a sub 2, that gives you a sub 1, negative a sub 2. That's what we just did. So whenever you see this where the right-hand side just switches sign, whenever there's a transformation, it is a reflection over the x-axis. You learned this in 8th grade or 9th grade or 10th grade. You learned it sometime, okay? But now we're going to see, is this a linear transformation? Similarly, let's say you were trying to do a reflection across the y-axis, something like this, okay? You will notice, so this is a reflection across the x-axis. You can also have t, reflection across the y-axis. Let me call this x, so you know it's across the x-axis. This is across the y-axis of a sub 1, a sub 2 is going to be, because it's across the y-axis, the y stays the same. So it's going to be negative a1, comma, a2. Now, will this be a linear transformation? We might be able to do a quick check of this, okay? Is a reflection a linear transformation? I think I'll do this, and I'm going to leave you with rotation and projection. Okay, the projection is easy. The one that would take a lot of writing is the rotation, and that's the one I like to give you. Okay, let us show that a reflection is a linear transformation. As you can see, I've chosen reflection over the x-axis, and so t takes points, takes point from R2 to R2, and this is what you have. We want to show that t is linear. Now, for full disclosure, I have never done this in my life before, so I'm doing it right on the spot. But because I know what we're supposed to do, it will be easy to do. We just need to say that we want to show that t is linear. So if t is actually linear, we're going to show t of c times a1, a2 plus b1, b2 will be equal to c times t of a1, a2 plus t of b1, b2. Okay, if we can show that this is the same as this, then we're good. So what I'm going to do is I'm going to do this side and I'm going to do this side and see where both of them become the same, and I'm going to stop. Or I could go from one to the other. I think I can go from one to the other. I like doing that actually. It's extreme algebra, but it's sweeter. So here we go. What is this transformation based on this? Well, we're going to have t of, this is going to be top. You know what? I'm going to multiply this out. So it's going to be t of CA1, comma, CA2 plus B1, B2. Okay. Now, because they're vectors in the same vector space, I can add the corresponding components. So this is t of CA1 plus B1, CA1 plus B1, okay, comma, you have CA sub 2 plus B2, okay. So I've added corresponding components. Now, so what do I get from here? By the way, you can do the vertical. That one makes it easy even. Okay, but let's leave it. So here we go. Now, what is the definition of the transformation? The transformation, let me put equal to here. Yeah, I'm going to divide this. So the transformation we're expecting is that this is going to stay, but this is going to become negative. So we're going to have this to be CA1 plus B1, comma, this would be negative CA2 plus B2. That is what we expect to see when we have this definition of transformation. What can we do with this? Well, we can distribute this negative. You see how I'm not skipping steps. So the problem, I lost a lot of points in linear algebra because I was doing it as if it was linear, as if it was algebra. So algebra I could have skipped, I could have distributed immediately, but don't do 2 steps at a time. So this negative will be distributed, and don't add yet. So we're going to have CA sub 1 plus B1, comma, you have negative CA sub 2 minus, or let's write it as plus, negative B sub 2. Okay. Now I can start undoing the things I had done before. So this is going to be CA sub 1, comma, negative CA sub 2. Then we put this together, plus B sub 1, comma, negative B sub 2. Okay. Now I can take this C out. This is going to give me C times, here I have A sub 1, comma, negative A sub 2. Then I have plus B sub 1, comma, negative B sub 2. Okay. It looks like what I have here, this is the transformation of this right there. So it is, this is it. So, which is equal to what I was looking for. This is C times the transformation of A sub 1, comma, A sub 2. And this is plus the transformation of B sub 1, comma, B sub 2. Done. So we can say T is linear. Okay, I don't have space, but that's it. This is the process for it. Let's talk about projection. I think this is the easiest of all the 3 that we've done because we're going to be using some nice zeros. Okay, so what is a projection? Look at this guy. This vector has both the vertical and the horizontal component, but sometimes we're not interested in y. We just want the x portion of it. So imagine getting a flashlight and placing the flashlight directly above this vector. The shadow of the vector is only going to be cast on this part. the part that the light cannot hit. The length of that shadow is always exactly the value of the x-axis. So if you project this onto the x-axis, so the projection of this vector onto the x-axis will only give you x. Nothing else will survive. The y-axis is going to vanish. So the projection of a vector onto a certain component only retains that component. Any other component that is not in that direction vanishes. So we can say that the projection, let's say this is a projection. I'm going to just write it this way. The projection of 3, 2 onto, let me put it here. Projection onto the x-axis. Okay, let me say it this way. The projection of this vector onto the x-axis will only give you the value of the x-axis. This guy becomes 0 because it's flat. It's a shadow. It has no height. It has no vertical component. Only this will survive. That will be the projection. And if you project it onto the y-axis, and this survives. So always imagine a flashlight flashing in that direction. The shadow is going to be cast, and the length of the shadow is basically the length, the component of that vector that when you resolve it, that's where we're going to do the Gram-Schmidt process, because that's where you get the component along a particular direction. You see, there's a long way to go. So here we go. That's it. So is this a linear transformation? That you can easily test. Okay, remember what you want to test. A projection is the projection onto a certain axis. Let's say you have a sub 1 and a sub 2. If this gives you a sub 1 comma 0, then by definition, this is a projection onto the x-axis. If it switches and this is the 0 and this is retained, it is the y-axis. You should be able to see that once you start seeing something vanishing. If something vanishes from if one component vanishes, even if it's a 3, look at this. If you have t of, let's say you have x1, x2, x3, and what happens is you have this being equal to x1, 0, x2. This is the x, y, and z axis, okay? Then it means that you're projecting onto, you see it? That's it. So you can do your experiment with this. Just do this. Is this a linear transformation? You want to check this. Well, the projection of a1, a sub 2 plus b1, b sub 2, will this give you, remember this transformation, will it give you the same answer as t? No, I probably got to put a c here. Figure it out yourself. Okay, I got to stop this video. Never stop learning, because those who stop learning, stop living. Bye-bye.